Good morning, students. Um, good to be with you this morning. I just wanted to make a video recording since we didn't get a chance to see each other this week. Um, just to let you know, the schedule that I was given at the beginning of the year, there was a little bit of an error in it, and I apologize for this. I was expecting to see all of you on this Thursday. So the 24th of October is what I was originally given as a date when I would see the honors class. Your principal, Mr. Sandstrom, informed me, however, that you were actually in class on Wednesday this week. So that was a little error. And I'm going to see if I can make sure I get an accurate schedule for the remainder of our sessions this semester. But I just wanted to apologize for the lack of you being able to see me. And that's mainly the reason why I'm making this recording for you tonight. So a couple things I wanted to go over before we get into the topic I wanted to talk about today is just some of your concerns that I've been hearing about. So I know that many of you are concerned about grades and your performance in this class. Let me just reassure you that if you've been working hard and getting things done on a consistent basis, you have nothing to be worried about. I sent a progress report for each of you over to Mr. Sandstrom and Dr. Doyle this afternoon. And many of you are actually doing fairly well in the class. I'm going to send the same progress reports out to you and your parents tonight, just so that you can have a brief glimpse into kind of how you're doing. But the most important thing is not to get hung up so much on whether or not things are getting graded correctly. You leave that all to me. I mean, you feel free to email me and ask me questions about grades and let me know if things are incorrect. But I really need you to worry about keeping moving in the class, because that's the only way we're going to make it through to the end of the semester together. Okay, so to assist you with that, I want to make things as easy as I can for you. So it was brought to my attention this week that a lot of you haven't really been able to turn things in due to due dates cutting off your access to certain assignments. And, you know, I guess I should have anticipated this because we had agreed that we would kind of give you a nice week and a half to get things done. So there was a few assignments that I was emailed about that you were no longer able to access because the cutoff date had already passed. I get it. This class can be pretty tough, especially with you only having access to me once a week. So I'm going to reopen all those assignments for you so that you can resubmit them if you desire, because I know that those scores will help you in the long run to get a really good grade out of this class. And I just want to re-stress the importance of keeping moving in this class. So I will continue to give you suggestions, very firm suggestions on when I would like things to be done by. If you need more time, all I ask is that you please give me notice that you're going to need extra time. I haven't really heard from any of you requesting for extra time. So when that was brought to my attention that a lot of you are still kind of behind, it was a little bit shocking. So I'll reopen those assignments, but please in the future, if you know you're not going to be able to make a deadline, please let me know so that I know to leave the assignment open for you. Okay, enough said about that. So hopefully friction from last week went okay for you guys. I noticed a lot of you were submitting assignments in our course and to my email, and I will be grading those shortly. But I wanted to start to get into our next topic. Okay, this is topic number 6 that I wanted to talk about tonight. I want to keep this short because I know you guys value your practice time in class that you have. So let's just get started without any further ado. If we get time, maybe we can go through a practice problem or two. I found this really nice slideshow from a university online, and this slideshow parallels our textbook quite nicely. So I'm going to borrow it just so we can kind of go over some of the topics that you should have been reading about this week in your textbook. Yeah, if you haven't read about them yet, please do so soon so that you get that secondary reinforcement of these topics that I'm about to talk to you about. Okay, so to start with, topic 6 is all about circular motion, okay? Now, circular motion is defined here. Okay, so uniform circular motion is motion in a circle with constant speed, okay? So if you imagine this CD to the right in the picture, imagine you have a CD player that's spinning this disc at a constant speed, okay? That would be a great example of circular motion. Now we're going to be talking about some relationships and some equations that deal with circular motion. So the first thing that I want to talk about is theta, which is the Greek letter that represents the rotation angle that the CD is spinning throughout, okay? So you probably already know this from geometry or from trigonometry, but this symbol right here means theta, which is an angle. Okay, so from point A to point B, and maybe this CD is spinning fast enough that it makes this rotation all within like a millisecond. The disk is spinning through an angle that we call theta. Okay, so that's what theta means. It's a rotation angle. So let's talk about how we calculate the change in theta, or the rotation angle. Okay, so there's an equation written here on this slide. This is important for you to know. There's gonna be a lot of equations in this slideshow. I'm gonna do my best to kind of box the ones that I think are pretty important. This is gonna be the first one. So if you want to calculate the angle that an object is sweeping over as it performs its circular motion, you can calculate it using this equation. Okay, so change in theta, or change in angle, is equal to change in S over R. Okay, so delta S over delta R will give you delta theta. Okay, so you can see in the picture what these things stand for. So delta S right here, this is your arc length. Okay, so it's the distance along the curvature that your object is traveling. Okay, R, of course, is the radius of the circular path that the object is traveling in. And of course, once again, we see that theta is the angle that the object is making along its path. Okay, so that's an equation you want to have written down someplace important. Delta theta is equal to delta S over R. Okay, now just to talk about some units that you'll see throughout circular motion. One revolution around the circle is just one cycle all the way around the circle. Okay, we sometimes abbreviate this with rev. Okay, we already know that there are 360 degrees in a circle. You've probably known that since you were in 5th grade, but something that's a little bit more obscure that you probably learned back in pre-calculus or algebra 2 is that 2 pi is the radian measure of angles in a circle. Okay, so maybe you might want to brush up on what the difference is between degrees and radians on your own time. And if you haven't really taken courses where you've learned this, you probably should get it with me as soon as possible so we can explain this to you. Okay, so we can say then that one complete revolution around the circle is basically a revolution that's going 360 degrees all the way around the circle, which is the same thing as 2 pi radians around the circle. Okay, let's keep going. So here are some practice problems from this slideshow that you can use if you'd like. The homework doesn't really ask you that much to convert between degrees and radians, so I'm just gonna gloss over this real quick. You can see in this slideshow, oops, you can see in the slideshow that they paste the solutions to these practice problems in the notes section. So that would be a very useful study tool for you to use. But once again, these formulas are not too important for your success in this class. This is stuff you probably learned back in algebra 2 or geometry. Okay, so here's kind of the next slide with information that's important. So kind of picking up where we left off, we just gave you an equation for delta theta. You can see that we're going to talk a little bit more about delta theta on the right side of this slide, But on the left side, we have a new vocabulary term called angular velocity, okay? So basically a fancy term for how fast an object rotates. It's represented by the variable omega, which is that Greek letter that kind of looks like a W. And angular velocity is equal to the angle of rotation divided by the change in time, okay? And that makes sense because whenever we calculate a velocity, we always take a distance and divide it by a time. Okay, so that's not too bad. Going over to the right side of the screen, there's a lot of equations listed here. I don't want you to get hung up on how they're derived. Once again, it's my job to kind of box the ones that are important. So I'm going to box this one that we just went over. Really, and I want you to just notice that on the previous slide, we saw this equation. Delta theta equals delta S over R, okay? We can basically manipulate that equation and solve it for delta S, okay? And then what we can do is we can plug the resulting expression into our equation up here for velocity. So really, doing that yields this bottom equation right here. So this bottom equation is an equation for linear speed, okay? So I'm gonna get out my pen just so we can differentiate between all of these. Okay, so this equation over here is for angular velocity. So that's the one that's on the left side of the screen. Okay, the one that's on the upper right side of the screen is the one we covered in the previous slide. So this is angle of rotation. Okay, and then this bottom right equation that I've just boxed, this is your equation for linear speed. Okay, so those three equations that I've boxed, you're probably going to want to write those down, have them on hand as you approach the homework problems. There might be some equations that ask you very point blank, hey, what's the angular speed if theta equals this and time equals this? I tried to eliminate all the homework problems that were beyond the scope of what we're teaching you today, but just have these equations written down so that you can use them as you approach the homework. Now, down here, there's some information on the units. So angular velocity, it's measured in units of radians per second, okay? So just keep that in mind as you write down answers, that the units for angular velocity are radians per second, okay? And also, you probably learned this again in Algebra 2, but the convention for circular motion is that as we go counterclockwise, we associate that with positive direction. Going clockwise around the circle, we associate that with a negative direction, okay? And if you don't really understand what I'm saying, if you've ever learned about the unit circle in math class, you've seen the same concept. Going clockwise around a circle is considered going negative direction. Going counterclockwise is considered positive direction, okay? Let's keep going. Okay, so here's a practice problem. Once again, the solution's down in the notes to this slide, so you can kind of see how they get started. I'm just going to gloss over these again because we're kind of short on time. So this is just a practice problem that's having you solve for the angular velocity, which we just gave the formula for on the previous slide. It was that little omega equation. And they also ask you to solve for the linear velocity, which we gave you on the previous slide as well. Okay, so here's just kind of a little thought question. And this is kind of here to drive a point home about linear speed. Okay, so imagine that there is an object traveling along this circular path. Okay, so if we're going along this circular path right here, suppose for a second, like pretend with me that this is the path that a sling takes. I don't know if you guys have ever seen an old-fashioned slingshot, but if you're whipping something around in a circle, and let's say that you were to suddenly let go of that object mid-path, there are three scenarios that I want you to kind of think about. Do you think that if, like, let's say that you're slinging a stone of some sort. So here's your stone, and you're slinging it around the circular path. If you let go of the stone at this point at the top of the circle, would the stone follow path A? Would it follow path B, or would it follow path C? Okay. Most of you are probably going to understand that choice B is the most logical answer here. The stone's definitely not going to curve in a direction opposite to the curvature of the circle. That doesn't make sense. You might think that choice C makes sense because it kind of parallels the curvature of the circle, but the object in reality is not going to curve at all. It's going to go straight out in a direction that's tangent to the circle's path. Okay. That's how we can aim slingshots, because we know that when we let go of the rock or the stone, it's going to fly straight in the direction that it was headed in that instant in time. Okay, so just keep that in mind. Things always take a straight line path when they leave a circular path. Okay, these next couple slides could get a little hairy. So once again, I'm going to try and water this down as much as I can and just give you the need to know information. Pretend for a second like we have the slingshot example or some other circularly traveling object. If you take a look at velocity at certain instances in time, like at point O right here, at this instant in time, the straight line path of this object's motion would be going this way. A fraction of a second later, perhaps, at point P, its tangent line direction, its straight line speed is going this way. Okay. Now, why do we care about this? Well, some very smart people got together a long time ago, and they showed that when you take a look at the path of the velocity, it actually almost looks like an isosceles triangle to the actual physical path that the object is traveling in. So these two triangles right here, they are proportional to each other. They're similar, okay? And the reason why this is important is because we can use proportions and some fancy math. On this next slide, you can see we've got some proportion problems here. And this is kind of where I don't want you to pay attention to how we derive the equations. I just want you to pay attention to the final results. Okay, so once again, some really super smart people got together, looked at these two isosceles triangles, started comparing how velocity and distance compared between these two triangles, and they came up with an equation that talked about acceleration. Okay, so this variable right here, a sub c, this is an equation for centripetal acceleration. I'm going to type this for you. So this is your equation for centripetal acceleration. That's what a sub c means. Write this down. It's a boxed equation. Centripetal acceleration is equal to v squared over r. Now remember, v is the linear speed that we taught you how to calculate a few slides back. R is the radius. Okay. On the far left of the equal sign, we see another version of this equation. Okay, so another version of this equation says that a sub c, or centripetal acceleration, is equal to your radius times the square of the angular velocity. Okay, so be familiar with both of those equations, the v squared over r1 and the r omega squared equation, because depending on what you're given in a particular problem, you might use one, you might use the other. Okay, but that's an equation you're going to want to have on hand. Okay. All right. So this is a little bit of review, a little bit of new stuff. So once again, if a satellite, let's say, was traveling along a circular path, if it exited the circular path at this point in time up here, its linear speed would carry it in a straight line path from the point at which it left the circular orbit. Okay. Now, here's something that you might not have thought about before. Centripetal acceleration applies to any object that is moving around a circle. Okay. Now, what's really cool, but kind of mind-boggling at the same time, is that centripetal acceleration always points towards the center of the circle. So believe it or not, when this satellite is making this orbit around the planet, let's say, there's a centripetal acceleration that's always pointing towards the center. So, for example, let's say that we were at this point in the orbit at a particular time. At that instant, the acceleration was pointing towards the center of the circle. Okay, maybe a few seconds later, at this point in the orbit, at this instant in time, the acceleration was pointing towards the center of the circle. Okay, and then up here, where our satellite is apparently leaving orbit, at this point in time, it's got an acceleration that's pointing towards the center of the circle. Okay, so basically what I'm trying to get you to see here is that any object that travels in a circular path has acceleration that is directed towards the center of the path, the center of the circle, I mean. Okay, and that's going to become important when we talk about force in a moment. Okay, here's a little practice problem. This basically asks you to calculate centripetal acceleration. So feel free to look at that at your own discretion and solve it if you so desire. Once again, you'll use the equation for centripetal acceleration. Solutions shown down here in the notes. Okay, so the reason why it's important for you to know that acceleration always points towards the center of a circle is because Newton taught us a couple topics ago that if your acceleration is pointing in a certain direction, then your force is going to be pointing in the same direction. Okay, so force and acceleration, net force I should say, and acceleration always point in the same direction. So what that means is that when an object is traveling in a circular path, we already established that the acceleration is pointing towards the center, but that means the net force is also pointing towards the center of the circle. And we'll talk a little bit more about why that's important. Okay, but here on this screen, we have Newton's second law right here. We learned this 2 topics ago, force is equal to mass times acceleration. It follows then that if we're talking about centripetal force and centripetal acceleration, the relationship will look very much the same. Centripetal force is equal to mass times centripetal acceleration. Okay, now remember the previous slides, we gave an equation for A sub c. Okay, and that equation was that A sub c was equal to v squared over r. So you can see in this equation down the bottom, we've substituted v squared over r in place of A sub c. Okay, and so what you have as a result is you have an equation here for centripetal force acting on an object traveling in a circular path. Once again, I'm going to box it because it's important. F sub c equals mv squared over r. An alternate form of this equation is shown on the far right. F sub c is also equal to m times r times omega squared. Okay, so once again, be aware of what the problem is giving you that you're working on so that you can then pick out the equation that's going to get you where you want to go. Okay? All right. Almost done. Now, this slide kind of gives you a popular misconception about centripetal force. So pretend for a second that let's take the planetary example. That's kind of so famous. So pretend for a second that we have a planetary orbit. Let's say that here's the sun in the middle, or maybe let's call this the Earth actually. Let's call this Earth, and let's call this little box I'm drawing, let's make that a satellite. So if we have this satellite and it's traveling in this circular orbit, we already explained to you that the acceleration of that satellite as well as the force on that satellite are pointing towards the center of the circle, okay? So what that means is that as the satellite travels around the circle, it's being pulled towards the center of the circle because of that centripetal force, okay? Now, a popular misconception is that centripetal force is just a kind of like a phantom force. It's just created simply by the fact that something is traveling in a circular path. No, centripetal force isn't a new separate force. It's not a new separate force created by nature, okay? It's a force that lines up with other forces that we already know about. So it's just, what I mean is, it's not just the fact that the satellite is traveling in a circular path that's causing it to be pulled towards the center. Some other force is causing that centripetal force. In this case, gravity. Okay, we know that gravity is always pulling on something that's above the Earth. Okay, so as this satellite makes its circular path, the Earth is constantly pulling down on it. Okay, and at all points along the circle, gravity is pointing down on the satellite. So you can kind of see from this image that centripetal force is pulling an object towards the center, but it's not some new mysterious force that we can't explain. It's a force that's linked with an already existing force that we know about. Okay. Let's keep going. We have some other examples here that show you that forces come from already existing forces. Let's keep going though. So here's another practice problem, one that asks you to calculate centripetal force, or F sub c. Once again, the equation is, and the solution is shown in the notes in case you were wondering. These are great questions, by the way, because they parallel what you could be asked on the homework. So take a peek when you get the chance. Okay, so this is just kind of a thought question. If you think back on the equation for F sub c, okay, and let me just kind of refresh your memory on it in case you forgot. F sub c, or centripetal force, is equal to mass times linear speed squared over the radius of the circular path. Okay, so here's a thought question. Which variable affects centripetal force more? Would it, if we change the mass, would that have a greater effect on F sub c? If we change the radius, would that have a greater effect? Or would the speed change have the greatest effect? Okay, now the answer is obviously listed down here in a separate bullet point. But you'll notice that these three variables in the equation, out of those three variables, speed is the only one that's being squared. Okay, which means that if we change the speed of a circular moving object, that squared effect is going to vastly influence the centripetal force, way more so than changing the mass or the radius would. Okay, so speed is probably, I would say it's the main contributor to changes in centripetal force. Okay. Okay, so here is kind of a lead-in to a very popular homework problem that you'll see all the time in physics classes. It's the banked curve. Okay, so we're going to show you a picture of the banked curve on the next slide, but pretend for a second that you are driving a car at a very high speed and you're going around a curve that's really sharp. Okay, if you are traveling at a high speed trying to go around a sharp curve, your car might go so fast that it flips as you make that sharp curve. Okay, the reason for that is just because the momentum of the car might just be too powerful for the curve and the car might topple. So the way we prevent this from happening, and you've probably seen this at like NASCAR on TV or something, you'll notice that turns on like a racing track are banked. Okay, and banked just means that the turns are tilted. Okay, and the reason we do this is to kind of prevent that momentum from flipping the car as you go around a curve. Okay, so these 2 bullet points kind of explain what protects you from flipping. So in an unbanked curve, like what you might see in your neighborhood, friction is the only thing that keeps the car being pulled towards the center of its circular path. Okay, now I don't know about you, but if you're going really fast, you can't really depend that much on friction to keep you safe. Okay, when you bank a curve, like they do in racetracks, you rely on friction a lot less because the curve is banked, which means the angle with which the car is making with the horizon, it's steeper. It's not as shallow, so there's less tendency for the car to flip. You'll see this in a second when we show you the picture. But you don't have to rely on friction. So the reliance on friction is eliminated for a given speed when you bank a curve. Okay, so let's show you what this whole banking thing's about, in case any of you don't really know what I mean when I say banked curve. So here's a great picture. Here's our little race car. It's going around this track right here. Okay, you can see that whoever constructed the track made it so the asphalt is kind of at an incline with the horizontal ground. Okay, we do this because, once again, the shallower that angle is, if it was really close to the ground, then the only thing keeping that car on the ground and going a circular path would be friction. Okay, so when we bank the curve, we take away some of that dependence on friction, and the car is able to navigate sharp curves a lot more smoothly. Okay. Now, here's again one of those moments where I don't want you to get hung up in how these equations are derived. Okay, we'll leave that for the people who came up with these, and I'm just gonna go straight to the equation that I want you to know. Okay, so on the next slide, I want you to box this and put it in your notes. Okay, so right here, this is an important equation. So this equation says the tan of theta is equal to v squared over r times g. Okay, so theta, if you look back at the picture of the banked curve on the previous slide, the theta we're talking about is this angle right here, the angle with which the road meets the horizon, the flat land. Okay, so that's your theta right there. You already know that v stands for linear speed of the car. R stands for radius, obviously. Remember our old friend g from topic 3. G is equal to negative 9.8 meters per second squared. You already know that. Okay, but what is this equation? Why do we care? This equation is there to help us determine the optimal speed for going around a certain angle, or it could be used oppositely to figure out the optimal angle that a road must be banked at to navigate it at a given speed. Okay, so let's show you a classic example of this. So remember that equation. Hopefully you had time to write it down. But here's a practice problem. There is a practice problem very similar to like this on the homework for topic 6. So FYI, what you see here can help you a lot. So this practice problem says, in the Daytona International Speedway, the corner is banked at 31 degrees and the radius is equal to 316 meters. What is the speed that this corner was designed for? Okay, so you can see down in the solution for this problem, they've written the equation down here. It's basically just plugging things in, solving for what you don't know. So your theta they gave you is 31 degrees. Okay, so that's going to go for theta. They're telling you that the radius is 316 meters. That's going to go in place of r. We already know that g is 9.8 meters per second squared. And all you got to do is get v by itself using algebra. Okay, so pretty easy equations. And just in case you were curious, if the track is banked at 31 degrees with a radius of 316 meters, the race car's maximum speed with which they could go around that curve would be about 43 meters per second. Okay, this is really cool really cool that we know all this stuff. This is how we design racetracks and roads, okay? And this isn't just racetracks. Like, you've probably all seen that for a very sharp curve, sometimes construction workers or city workers will slightly bank a turn so that it is a little bit safer for cars that are going around it. Okay, it's just really cool stuff we're learning. I hope that you feel the same way. Okay, this slide is just kind of repeating what we've already said. Whenever objects leave circular motion, they go in a straight line. Okay, because of Newton's first law, objects in motion want to stay in motion. So it makes sense that if an object is traveling in a certain direction, when it leaves orbit, it's going to keep going in that direction until acted upon by some external force. So that's just kind of a rehashing of what we already talked about. Okay, so here's some real life examples of this concept. Okay, so the little thought question, how does the spin cycle in a washing machine work? So speaking of things leaving circular paths in a straight line, when a washing machine is rotating its drum, okay, so you've got your wet clothes in there. The drum is rotating, and then your clothes are clinging to the sides of the drum. Okay, so like here's your laundry. Maybe it's like your shirt or your sock or something. Okay, and then if you've ever looked inside a washing machine, you'll notice there's little holes in the drum of the washing machine. The reason the holes are there is because the water droplets that are clinging to the sides of the drum in the washing machine, they're tiny, okay? So as the clothes travel in a circle, the water leaves the circular path in a straight line and goes through the holes, okay? And basically you're just flinging water out of your clothes in a straight line path. Okay, so that's kind of a real life example of how we use that straight line path to our advantage as an object leaves circular motion. Last slide of the day. This is kind of a more silly example of the straight line path concept. So this says, remember the good old days when cars were big, the seats were vinyl bench seats, and there were no seat belts? Maybe this is back in like the 50s, I don't know. Well, when a guy would take a girl out on a date and he wanted to get cozy, he would put his arm on the back of the seat and then make a right-hand turn. The car and the guy would turn since the tires and the steering wheel provided the centripetal force. The friction between the seat and the girl was not enough. So the girl would continue in a straight line path while the car turned underneath her. She would end up in the guy's arms. Basically the same thing that happens whenever you go around the sharp curve in a car. You slide across the seat because your body just wants to keep going in the direction in which it was going around the curve. Okay, so I know this was a little brief for all that we went over today. So I would encourage you to go back and read the text for this topic to kind of reinforce these concepts. If you have questions or if you need some clarity, please do not hesitate to email me. And we can go over some things. But we learned, probably a good 5 or 6 equations from this presentation, so please have those written down. You will use them in the homework. And homework is not too bad this week. It's really just maybe 4 or 5 problems per assignment. I think there's like 2 or 3 assignments. So I really hope you guys are starting to enjoy this class as far as the workload is concerned. It is a lot lighter than it used to be. And that's going to make my job easier to grade it. It's not going to make your job easier to do it. So let's keep moving. Let's have a good time. Thanks, guys. I hope you have a good weekend, and we will see each other next week. And I will get that schedule worked out so that we don't miss each other like we did this week. Let me just figure out how to stop the recording real quick, and then we will call it a day. Thanks, guys. We will talk to you later.